Hi, this is Greg from Structural Toolkit, and this is the sixth and final video in our two-story residential house design series. In our previous video, we went through our brace frame design, and now we're up to designing our concrete raft slab, our front masonry fence, and the timber sleeper retaining wall to the rear. We'll go through the raft slab first and cover the fence and retaining wall later in the video. You can use the chapters below to skip around as needed. Now, depending on the kind of footing system you need to design, your approach to designing it will likely differ a bit. Determining the most appropriate footing system is heavily dependent on your soil profile. We spoke a bit about our soil profile in the first episode, where we first set out our slab. So we'll give a brief overview now. Based on our soil report, our site is Class M, and we have roughly 200mm of fill over our sloped site, with our underlying founding material being sandy clay. There are no nearby existing trees or trees that will be planted. Under these conditions, a deemed to comply raft slab from AS 2870 would be appropriate. We'll be founding the beams directly into our sandy clay founding material. In our first episode, we went through in detail the various rules and requirements for the set out of stiffening beams in a raft slab, and so we won't be covering that part of the design again in this video. As the site is slightly sloped, we will be building the site up a bit in areas. This, alongside there being 200mm of fill, we will be exceeding the 400mm fill limit as specified in AS 2870 clause 2.5.3 for in situ and non-sand filling. There are a few solutions to this, such as engineered fill, or by removing the fill and building up in compacted layers as specified in AS 2870 clause 6.4.2, or by designing the slab as suspended, or in other words, designing the slab so that it can span from beam to beam with no support of the soil underneath. Engineered fill is uncommon for residential projects like this one, so it will likely be more appropriate to go for a suspended slab. The first part of a slab design is working out where we need to suspend a slab panel. Although a simple approach would be to suspend the entire raft slab, if there are significant portions of it that don't need to be suspended, then this isn't very economical. That being said, the designer will also need to consider the varying performance of on-grade versus suspended when it comes to differential movement. A good way to work out where we need to suspend a slab panel is by calculating the levels of fill below points around various panels. To do this, we can use our finished floor level, contours and fill measurements to work this out. On our plan, we'll start with the bottom right of our raft slab. Here we have a finished floor level of 54.25. To get to the start of our saw, we'll take off 100mm for the slab. This brings us down to 54.15. Now we need to work out at what level our fill ends. Looking at our contours, we can see our natural surface is about 53.65. We'll then need to go down 200mm from this to account for fill, which brings us to 53.45. So taking our first calculated value of 54.15 and minusing off our 53.45, we get 700mm of fill. So we know as this edge exceeds 400mm, we'll need to suspend this panel. Going along to the next stiffening beam, we calculate out the fill to be about 600mm, then 450 and finally 350. As we've now gone below the 400mm limit, we know we can stop our suspended slab panels here. However, as our natural surface level isn't uniform going from south to north, we'll need to calculate a few extra points to get a full picture of where we need to suspend. It's also worth noting that our garage floor steps down 100mm from the rest of the slab. With the rest of our points calculated, it will be useful now to draw a line to clearly show the point where fill goes beyond 400mm. As a side note, a quicker way to go about this would be to just calculate the level where we need to suspend directly and then draw a line based on that. We went about it in a more detailed way just so it's clear what we were doing. We can see that about half of our garage has more than 400mm of fill, and where we step up, the 400mm line extends into in front of the stairs. Any slab panel that's on the right of this line, or even crosses it, will need to be suspended. We'll need to keep in mind that all these numbers here are somewhat approximate, so we'll want to stay conservative where needed. With that in mind, we'll be wanting to suspend our slab panels up to here for the upper level. For the garage, although technically we could skip the upper left panel, as it's quite small, it's going to be easier just to keep it consistent with the rest of the garage, and so we'll suspend it as well. So that it's clear which panels we are suspending, we'll also add a hatch to them. With our suspended panels determined, we can look at designing them. We'll be designing them as a two-way slab, using the two-way slabs and concrete member design modules. We've done a video on this kind of design previously. There will be a link to it in the description below, so have a look at that if you're unsure about any part of the process. We'll want to be selecting panels that will have the highest positive or negative moment in them. The highest negative moment is often found with a corner slab panel with two discontinuous adjacent edges, or a panel that only has a single continuous edge, being similar to that of the first span of a multi-span beam. The highest positive is then usually where there are no continuous edges. As you would expect, the bigger the panel size, the bigger the moments are as well, so there are a few things to consider. So keeping that idea in mind, we'll pick a few slab panels to design. We'll also need to remember that our floor, dead and live loads will be different for our garage and the rest of the house. The first panels we'll look at will be in the garage. An obvious first choice will be one of the two large panels here we have in the center. Switching over to our SDK project, which we've been working on in each episode, we'll create a new section to the left and call it Slab. In here we'll open up our first two-way slab document. We'll be using a typical concrete strength of 25 MPa and a slab thickness of 130, which is a typical thickness for a suspended slab panel in a residential house like ours. Our reinforcement ductility class will be L, as we'll be using SLA2 mesh or similar, depending on what our design ends up as. If we measure from center to center of our slab panel lengths in both directions, we can see our long edge length is 4 meters, and our short edge length is 2.5. Our continuous edges are 2 for both in this case. So for a garage panel, you'll have a live load of 2.5 kPa, but as our garage will have no floor coverings, our superimposed dead load will be 0. Down below for our deflection, we'll select our SLA2 mesh for now. A cover of 30, and input our compression steel as the same for good measure. We'll be using a deflection limit of span on 250 for total span, and span on 500 for incremental, which comes from table 2.3.2 of AS 3600. Incremental deflection is the deflection that takes place after the addition of the brittle partitions or finishes. We can see our deflection for this panel is okay. Looking at our moments in our panel, we get a maximum of negative 3.6 kilonewton meter per meter and 1.8 kilonewton meter per meter for positive. Our next slab panel will still be in the garage. We'll pick our corner panel here, which has a few discontinuous edges. This may provide us with a greater negative and positive moment. Measuring the geometry, we have 3.5 meters and 1.8 meters. To make things easier, we'll just copy our first panel document and change the inputs as needed. As we can see, our continuous edges are 1 for each way. This time we get a maximum negative of 2.8 and positive of 1.6. Next we'll pick a panel that isn't in the garage. We'll pick the panel at the front of the house here, which measures 2.5 metres and 3.25 metres. Skipping ahead, we can see this panel gives us moments of -3.3 and 1.6, which means that our first slab panel had the greatest forces. However, one more panel we should look at is the garage panel at the rear that's adjacent to the first panel we checked. Here, instead of having 4 continuous suspended edges, at the step our suspended panels stop. Now, although this could be detailed such that the top reinforcement is sufficiently lapped, making it such that the edge becomes somewhat continuous, as this slab panel will be thinner, it's just going to be easier to first check if our design works as it being discontinuous. So we'll copy our SL01 slab document and set our continuous long edges to 1. This gives us a maximum negative of 4.6 and positive of 2.4, meaning this is our critical slab panel. The next step is to then perform a design check of these moments. We'll start by opening up a concrete member design and call it slab design. We'll enter in the same geometry values as we did before. Our slab type will be T, referring to two-way and walls. Our span isn't relevant for the design we're doing, so we'll leave it as is. We'll input our reinforcement first, then look at our moment input. As discussed, we're going to try using SL82 mesh top and bottom, and for our cover we'll use 30 top and bottom. So as our reinforcement is the same top and bottom, we actually only need to check our moment of highest magnitude, which if we input as 4.6, we can see works comfortably. Because the bars actually cross each other, the cover to the tensile bars in one direction will be different to the other. So for designs that are close to full capacity, it will be something you need to account for given that the direction the mesh is laid on site is generally not known. If you had to use reinforcement that wasn't the same top and bottom, then you'd create two documents with one being for negative and the other being for positive bending. Alternatively, you could use the snapshot feature, which allows you to store the two sets of design data in the same document. You'll find that the negative moment is generally always larger, and occasionally you may need to increase the mesh size to accommodate that. With our slab's moment capacity checked, the final part of the main house is to then check that the soil under our edge and stiffening beams has sufficient bearing capacity. One way to do this, in a similar way to how we previously did our column loads, is to set up a plan with all our column reactions on it, which we prepared a few episodes ago. And at critical locations, calculate the total force per metre length of a slab beam. If our bearing force is greater than our bearing capacity, then we'll need to look at adding a pad footing in that location. Our soil report states that our founding material is sandy clay. In this material, we get a 150 kPa bearing capacity for founding slab edge beams, pad footings and strip footings, and that the footings need to be founded at least 200 mm into this material. We'll be using this bearing capacity then to check our slab beams. For a classification of M, we're using a concrete rail slab and articulated masonry veneer. We'll be looking at edge and internal beams that are 400 deep and 300 wide, being based on figure 3.1 from AS 2870. This means we'll get 150 kPa by 0.3 equaling 45 kilonewtons per metre of bearing capacity for all our beams. We've put this on our footing loads plan to keep things clear. Some critical locations to think about will be wherever we have a suspended slab, as this slab will be supported on a beam, and also where we have a high column load. What we'll first try then is our EB1 on the garage external wall to the north side, where we have a point load. On this edge beam, we'll have a combination of roof, brick veneer wall, suspended slab, and also the footing itself. Measuring our floor to top of wall, we get about 3200. Obviously our brick may go down further than this, but we'll just absorb this into our footing weight. Our roof is about 950. For our slab, we'll need to remember that it is two-way, and so it's not always appropriate to take half the span, as this may be a significant overestimation of what the actual load would be. In our case, to demonstrate, we'll draw lines at 45 degrees from the corners to see exactly what our distribution would be like for our EB1 here. As our slab panel is quite long and slim, in this case taking half the span will be appropriate, as we can see. We'll take our edge beam slab weight to be to the face of the footing in this case, as the additional live load miss that would be on our edge beam here is negligible. For an internal beam or an edge beam with just light clad stud, you probably wouldn't do this. Here we can measure out 750mm. Finally, we have our footing, which is 300 wide, and although the minimum depth is 400, at this location we have a bit of fill, and as we'll need to fan down at least 200mm into the founding material, we'll need a footing about 750 deep from floor level. So there will need to be some level of blinding concrete below our 400 deep edge beam. So for our footing weight, we'll take it as 750 by 300. Summarising these lengths into a list here, we can then calculate out their weights. For roof, it's 0.4 kPa dead and 0.25 kPa live. This gives us 0.4 kilonewtons dead and 0.2 kilonewtons live. Continuing on, we have 2.6 kPa for wall weight, and for our slab will be 3.25 kPa for dead, with no superimposed 0.5 as it is garage, but then 2.5 kPa live. Refer to our previous episodes for further explanations on material weights used. We then have our footing, which will be a 25 kilonewtons per metre cubed weight. There is the argument that you can just use 6 kilonewtons per metres cubed, as you are removing soil to add the footing, with 6 being the difference in density from soil to concrete. But care should be taken when the edge beam is founding through predominantly fill. We'll see how we go without this reduction for now. Finally is our C1, which we already have the forces for. Calculating out all our forces gives us a total of 29.8 kilonewtons per metre dead and 12.1 kilonewtons per metre live. The total of this is less than our capacity of 45, so we are okay for this edge beam. Where a point load is supported on an edge or internal beam, the point load distributes within the footing over some length. For simplicity, we have used 1 metre or 500 each way. If we look at section 12 of the concrete code, it refers to a non-flexural member having a cantilever of 1.5D, so you could probably justify 3D. We'll do a few more of these and see how we go. The process will be the same for the rest, keeping in mind that our beams to the left won't have a slab component as they aren't suspended. Skipping ahead, we've completed 2 more critical locations. One under the C1 being the garage and entrance, which came out to be well under capacity, and also one in the back living room under the C1 here. We can see this one did get close to our 45 kilonewton limit. However, our approach to working out our loads here is conservative, so there are a few things we could try to reduce our loads if needed. For example, our load is per metre, directly under the column. We have 500mm to the left that is load bearing and 500mm to the right which is just a window load under the lintel the column supports. So you could argue that anything from above the ground floor will only contribute to 500mm of the 1 metre strip. So we could halve our roof, walls and floor loads from above, though we would still need to keep some amount of the wall to the right as we still have the window. Other options we have for refining our loads include AS 2870 allowing the use of half the live load as per clause 1.4.2a for bearing, or possibly looking at the density of our footing not being 25 kilonewtons per metres cubed due to soil removal as we discussed earlier. If you end up not being able to get your beam to work, then you would need to look at providing a localised square pad or similar within the raft slab, in order to increase your bearing area sufficiently. You should also be conscious of having too great a differential of bearing pressures under the footings, as this may lead to differential settlements. For our slab here, These 3 checks should be sufficient for our bearing. This then finishes off the design of our 2-storey house, with all that's left being our external retaining wall and the front fence. First we'll start with our sleeper retaining wall. The first thing we'll want to work out is our maximum retaining height. The backyard will be levelled to 300 below the internal floor height, so at a level of 53.95. Looking at our contours, we can see at the corner we get up to about 55.3. So our maximum retaining height is about 1.35 metres, which will round up to 1.4. Often the building designer will specify a maximum required retaining height as well, which you should always check against the contours. We can see our retaining wall height will vary along the boundary, so we will probably do a couple of design options for different heights. So we'll first start by creating another section called retaining wall. In here we'll open up a sleeper retaining wall module and call it sleeper wall RWO1 1400 to indicate its maximum height. We've done a video on this module previously where we designed a concrete sleeper wall. A link will be in the description below, so check that out if you're unsure about anything. The version of the module we are using now has been updated a bit since that video, with there being a few newer options available for the footing overturning check. So starting with our geometry, our retaining wall height is 1400. For our post centres, 1800 is a good place to start, but we can decrease it later if deemed necessary. Our uprights will be steel and our sleepers will be timber, so we can leave these options as they are. We'll be using a typical 100 UC upright with 100 by 200 F5 sleepers. Our risk class will be left with B as we are on the boundary. Next we have our soil parameters for behind the wall and then around the footing. Our geotech has provided us with some retaining wall design parameters for the different layers of soil on the site. Our 200mm fill layer has no parameters. For our sandy clay we have a cohesion of 35 kPa and internal angle of friction of 30, with a factor of safety already applied. We already have 30 degrees in our soil behind the wall, so we'll leave it as that. On the other side of the boundary, the soil level will be flat, so we won't have any incline. Now, although we have been provided with a cohesion value for our sandy clay from 200mm down, providing any amount of cohesion to the soil behind the wall will have an extremely significant effect on the overturning moment induced. Applying just a small portion of this cohesion will effectively negate the entire overturning moment in our case, being a result of the developed crack depth that occurs in the drained state. A typical approach taken here is to use zero cohesion. In reality, even if the wall is constructed in an area where the soil is cut near vertically, there will always be some level of non-cohesive or granular backfill used to fill out the back of the wall. So for now we'll leave this input as 0. For our footing depth we'll put in a tentative 1800 and ignore 200mm of topsoil. The amount you ignore is affected by the ability of the founding clay material to dry and shrink. This amount will vary depending on if the area is paved, unpaved, topsoiled, etc. We'll keep our footing diameter as 450 for now, as this is a typical size. Our cohesion for the footing is then 35 kPa. This is modified further by a reduction factor for in situ soil of 0.7 from AS 4678 Earth Retaining Structures Table 5.1a. Now, as our sleeper wall is next to the boundary, it will have a fence attached to the uprights. This means there will be an additional wind load from the fence we need to consider in our design. We'll use the calculator to the right to work out what this force will be. Our fence will be 1800 high. Our wind load is already in there thanks to the project values we set up in an earlier episode. We did a video on how to do this previously, so check that out if you're interested. We could look at refining this shape factor, but we will adopt 1.2 for this case. As we already have a load factor input to the left, we'll link the thrust and overturning cells to the base shear and moment values. The rest of our inputs here are fine as they are. Going down to the bottom, there are a few additional options for the overturning check. The important one for us is where our overturning moment is resolved to. Hoskin's method appears to apply the moment at the top of the footing and ignores shear. However, a more conservative approach will be to resolve this shear to the centre of rotation. In our case, we won't be resolving our forces to the centre of rotation, so we'll turn this option off. We have a document on our website covering this option in more detail, so check that out if you need. Going back to our design above, we can see all our checks are okay, and so we can probably reduce the depth of our footing. In our case, we'll reduce it down to 1500. Next, we'll want to design a shorter retaining wall that won't need as much footing embedment. In our case, a good height might be 1 meter, so we'll copy this and name it accordingly. For our 1 meter high retaining wall, we'll be able to reduce the footing down to 1200. For a retaining wall like ours, 2 options will probably be enough. So our final design of our series will be the front masonry fence. There isn't a retaining aspect to it, so it'll be purely designed as an overturning structure due to wind. We did a similar design for this in a previous video, so check that out if you're unsure about any aspect of it. To complete the design, we'll be using the hoarding, masonry member design, and eccentric pad design modules. We'll create a new section to keep things organised and call it fence. We'll start with the hoardings module. Our wall is going to be 5 meters wide and 1800 tall from ground level. To account for some level of built-in tolerance and the fact that the bottom of the wall will be 75 to 100 mil below the ground, we'll design for a max of 1900. This gives us a CPN of 1.23. Next is the masonry member design. Our wall is double brick with 80 mil cavity. We'll pick a 25 MPa compressed brick, noting that you must specify this compressive capacity on your standard drawings. We'll input our 2 leaves and put in a cavity width of 80. We'll start with looking at a fully grouted but unreinforced section, so we'll need to click the grounded button to the right. And for now, leaving our reinforcement input as 0. Next on our geometry tab, we'll put in our length of 5 meters, our height of 1900. We'll be doing 3 on both sides and the top. And rotational on the bottom. There are no warnings at the moment, but if we increase this fence to 2700, we can see that a warning comes up stating that the unreinforced wall is too slender. As for robustness, a minimum of 0.5 kPa must be applied, resulting in a moment of 1.82 kilonewton meters, being greater than our capacity of 1.8. Next, we'll be looking at our unreinforced bending tab. Our moment will be based on our cantilever wall with a wind UDL applied to it. This will be WL squared on 2, which we can calculate in our cell. For our wind pressure, this will be 0.68 times our shape factor of 1.23, which forms our UDL component. And then for L squared on 2, our length will be 1.9 to the power of 2 on 2. This gives us a moment of 1.51 kilonewton meter per meter. So that it's clear what we've done, we'll make it a comment. For transient loadings such as wind or short-term forces, AS 3700 clause 3.3.3 AIA allows a FMT of 0.2 MPa, which allows the fence to cantilever unreinforced with a capacity of 1.8, meaning our unreinforced design is okay. However, something we need to consider is that footing movements and small impacts can quickly compromise the capacity of the brickwork to have no capacity. So we will now look at the capacity of the fence with an N12 bar every 1200 millimeters. This gives us a capacity of 5.14 kilonewton meter per meter. This option works comfortably and will be the design we will go with. You may also want to consider providing horizontal reinforcement. Next is then our footing check, which we'll be using the eccentric pad for. The eccentric pad has been updated a bit since we did the video on it a while back. We now have some more comprehensive bearing calculations for footings with larger eccentricities in both directions, along with shear and moment along the footing. For our design, we'll start with a width of 600 millimeters and see how we go. For our length, we'll be going with 1 meter to keep it with our forces also being in a per meter length. For our depth, we'll go with 600. A Class M strip footing with articulated double brick above specifies 600, so for our reinforced wall, 600 will be a suitable depth. Our allowable bearing pressure is 150 kPa. Our first force will be our dead load due to our brickwork. This is 300 mm thick and 1.9 meters high. We'll use 22 kilonewtons per meter cube density, noting the density of clay bricks can vary from 1500 to 2000 kilograms per meters cubed. But we also have 80 mm of concrete grouting. This gives us 12.5 kilonewtons per meter. Our next load is then our wind load. We'll copy the formula we used in our masonry wall design. As the ultimate factor is 1.5, we'll need to divide this formula by 1.5 to get it back to working. We'll also need to add the shear component, which will just be our UDL times our height divided by 1.5 again. We'll then set this as a wind load. We can see that our footing is working comfortably at the moment, so what we can try and do is reduce down our footing's width to say 400 mm. Any smaller than this is probably a bit too impractical for our double brick wall. As we don't have an eccentricity on our footing, it's able to work fairly easily for a smaller width footing than you might get if the wall was directly on the boundary. For our strip footing, we'll probably go with reinforcement similar to L11 or L12 trench mesh with 4 main bars top and bottom. For a 400 wide footing, you would provide 4 bars and then for each 100 wider an additional bar. In situations where the footing gets wider, you will need to use the bending moment and shear shown at the bottom to check for any required reinforcement. One way of doing this would be with clause 20.4.2 of AS 3600 for unreinforced footings, where you can calculate the phi MUO of the footing, which equals phi times 0.6 times the square root of FC times Z, making sure you use a depth that is 50 mm less than the total depth. With our masonry fence designed, we've effectively designed everything we need to for this project. At this point, you would start filling out schedules, drawing details and adding any additional notes to the drawings that are needed to appropriately convey our design through our drawings. For example, we would want to add a note to our slab outlining the slab thickness and reinforcement we have adopted, and dimension out our sleeper wall so that it is clear what size footing we have specified, and also the spacing of each upright. You may find that as you are detailing things that certain design sizes may not fit, and so you will need to go back and rethink things. A project like this can sometimes be a bit of an iterative process. There is a lot to think about even when just designing a typical two-storey house. And with that, we've come to the end of the design series. The making of this video series has been a significant effort by the Structural Toolkit team, and so I hope you have enjoyed watching it. If you have any questions, feel free to contact our support team via email or by calling us. As always, thanks for watching.